18, I think 12 or 14 layers of different materials, different doping and so on. So this is a very complex system. It is grown by, in this case, by so-called metal-organic chemical vapor deposition. So it's a very sophisticated method to prepare materials. And obviously the reason for this was that people could afford it because they could get good price sending to space. So this type of cells are using on satellites. So I guess if your TV works well, satellite TV works, it means that there is some solar cells on some satellite which power the satellite. So so of course there was a trend of desire to find something less complicated, to find a system which could do the same, but with at much smaller cost, and of course could be simpler. And one of the issues here is basically that you have very much different materials: germanium, gallium arsenide, and gallium phosphide on the top. So this makes it difficult. So in our work, we look at nitrides. Nitrides are compounds which are basically, these are compound semiconductors of group 3 elements like indium, gallium, aluminum, and nitrogen. And they have a very interesting property that they span very large range of band gaps, starting from aluminum nitride has a band gap of 6.1 electron volts, which is deep ultraviolet. Gallium nitride is close to visible band gap, and indium nitride was a mystery. Nobody knew really what's wrong with indium nitride. What happened is that everybody thought its gap was 2 electron volts, around 2 electron volts. However, it was not certain because nobody could get any photoluminescence from the material and so on. And gallium nitride or nitrides are very successful if you have I don't know if you have, but if you have so-called Blu-ray player, then this is something which is made of material around gallium nitride here. This is the blue laser. So but basically, this is a very successful material. However, if people were adding indium nitride, they found it's very difficult to make good material. Something was happening, something was wrong. So we did research several years ago on this material, and we discovered that basically people for about 25 years were completely wrong. In fact, the gap is much lower. Band gap is only 0.7 electron volts instead of around 2 electron volts, which was assumed. And I will explain why people were so confused for so long time. So we have the signature of the gap, energy gap at 0.7 electron volt. This is absorption. Absorption is increasing starting from 0.7. We see light emitted at around 0.7. And also we see so-called photomodulated reflectance, which is another indication that there is a optical transition at this stage. So that changed the picture dramatically. And so we said now when we change the composition, we go from indium nitride, which has gap 0.7 electron volt. We add more and more gallium, so the gap goes towards gallium nitride. And you see that it spans a very large range of gaps, starting from 0.7 and going up to 3.4 electron volts. And previously, of course, people thought that it goes from 3.4 electron volts and goes to 2 electron volts, but it has turned out to be completely wrong. So we all of a sudden covered the whole spectral range here with material of different gaps. And now when you look at compare it with the solar spectrum, it's obvious that this is a very interesting material because solar spectrum extends from about 0.5 electron volt to close to 4 electron volts. And our material has a gap which changes from 0.7 to 3.4, which is a very good match. Because when you look at the current technology, this is germanium, gallium arsenide, and gallium phosphide, they only cover this range. In fact, there is a gap here, which people worry about. And they are already very efficient. So in our case, we can basically have any gap we want. So the question was, can this material be made well enough to get all these gaps we need to optimize the performance. So first question was, why people were confused for so long? Why why researchers in so many places thought that the energy gap between united is so large? In fact, that it is rather small. So this shows on absolute scale position of the valence band and the conduction band in gallium nitride and indium nitride. And you see that there is a huge change in the position of the conduction band going from gallium nitride to indium nitride. And in fact, you see that the electron affinity of the conduction band is positioned 5.8 electron volts below the vacuum level. This is unknown for any other semiconductor. This is quite exceptional. Also, it has another effect. Semiconductors, as you know, semiconductors, when you can have defects. Defects are if you remove one of the atoms, if you add some atoms. So basically, mass crystal lattice, you have defects in semiconductors. And the average energy of defects is known like it's called Fermi level stabilization energy. So in gallium nitride, it is in the gap below the conduction band, this level. In indium nitride, it's in the conduction band. And this is really not so good in a sense, because what happens now is that that these defects which are produced can add electrons, can change the conductivity of this material. So the understanding of the role of native defects is critical if we want to apply this material for any practical devices. So what we did, we kind of spent some time studying defects. And to do this, we intentionally, we have material, grown indium nitride or indium gallium nitride, and we intentionally introduce defects. And the way to do it is basically you have high energy electrons, 1 mega electron volt, and you bombard your sample, and you're getting a lot of defects. You can use also protons, and you damage it even more, because the heavier the particle, the more damage. You can use even helium particles, and then they damage more, but damage is more extensive and less more localized in some cases. Finally, you can use even ionized atoms, but this is a very heavy damage in this case. So there is people know how to treat, how to look at this damage, because you are using different particles, so you have to somehow scale damage from neon to electrons, and that can be done to some extent. So the other reason why we did this was that we, in principle, thought that if we can make these cells, we can use them in space, because this is a lucrative market, and this is where you really can always start very well. So, of course, in space there is a problem with so-called Van Allen belts. Magnetic field of the Earth traps high energy particles in the outer space, and there are kind of belts of high energy particles, and these are some of them are far away from the Earth, 6,000 miles, but some are very close. And in fact, for some purposes, especially military purposes, some satellites have to fly around the Earth in this close vicinity of Earth, and these belts are very intense. So basically, whatever that goes there is really heavily damaged. And cells are exposed because they have to expose to the sun as well. So this is one other issue. We have to know how our material is affected by damage. So we did this and this shows basically how it looks. So you can damage with different particles, electron, proton, or helium, and scale the damage on the same scale. So basically this is displacement damage in electron volts per gram. So this is a unit of damage. But basically what it shows that if you take, let's say, gallium arsenide, gallium nitride, especially gallium arsenide, which is used in current cells, you see that this really it goes very quickly. The PL luminescence, photoluminescence is a measure of quality. If photoluminescence is high, the quality is still good. So you see that this photoluminescence in these materials is decreasing very rapidly at low doses. However, if you take gallium indium nitride of different composition, it goes unchanged for quite a while. In fact, it's surprisingly, in some cases, the quality is improving even with some damage, initial damage. But we know, understand. Finally, when you damage it heavily, everything is destroyed. And this is how the solar cell in space behave. Basically, solar cell efficiency of solar cell goes down also with the damage. And the kind of figure of merit is that if efficiency goes down by 20%, it is becoming unusable. So it has to stay within 80% of its original efficiency. And then, of course, the question is, how long does satellite live? And how much damage it can take before you have to replace it. So now, to understand what's going on in this material, I have to talk about this amphoteric defect model. Basically, if you take gallium indium nitride and gallium nitride, this is material which we are interested in. So, and this is the position of the conduction band and valence band. So an energy gap is the separation between this, and it goes up. Yeah? So let's look now at the Fermi level stabilization energy, is the energy of these native defects, which we are introducing. And you see that this level here is in the band gap in gallium nitride, but it is well above the conduction band in indium nitride. And it makes big difference because how defects in gallium nitride make gallium nitride insulated because they move a Fermi energy into the band gap. Defects in gallium indium nitride make indium nitride conducting. That's what we expected. So we thought we would check it with our radiation study. And the way it works is that when we take indium nitride, so we have indium nitride and slightly n-type, so Fermi energy is here. This is the conduction band. We start to irradiate it, and we produce more and more donors, and Fermi energy goes up to this level here, to this point. So when we take, on the acetate, when we take gallium nitride or gallium arsenide or any other gallium indium phosphide, most of the semiconductors, then of course the stabilization energy is in the band gap. So in this case, when we start with Z-type material, Fermi energy is in the conduction band. In fact, the Fermi energy now goes down to the band gap. So it shifts. So we know how we knew how what to expect in this case. And in fact, when we did irradiation, these are experimental results, we see that the concentration of electrons in the case of gallium arsenide and gallium nitride goes down, as expected, because Fermi energy moves into the band gap. However, when we do the same studies on material with high indium content, this is what Fermi energy is the conduction band, concentration goes up and saturates at certain level. And we know how it saturates, how it behaves as a function of gallium fraction, so basically as a function of composition. So now, what is happening with optical absorption? Because now we are moving this Fermi energy in the conduction band. So let's take indium nitride. Indium nitride should have a gap, as I mentioned, 0.7, this low gap, and absorption goes up when you increase the energy. And then you irradiate it slightly, and what you see is a kind of absorption edge shifted to high energy. Because and then if you irradiate it more and more, absorption edge shifts to high energy. Finally, it saturates. Those last two sets of points are almost the same, although the irradiation dose is different. And the way it works is, in this case, looks like this. That when we irradiate, we produce this defect, the electrons, Fermi energy goes up. So the lowest energy transition now is not this low, 0.7, but it is only from here to there, to a Fermi energy, because this is an unoccupied state. So this is almost 1.7 electron volt or something like that. And that's really what people were confused about, because they always have samples with high electron concentration, and they thought it is really band catch, and this is the gap of the semiconductor. In fact, they were looking at Fermi energy. So this is so-called Bernstein-Moss shift produces the change in it. And after you can model it, and you get kind of good explanation of how it behaves. And so now when you go to different, so this is how it looks in indium nitride. So we have this much is shifted. We can shift it by irradiation that much. Now we go to different composition. We change composition. We have sample now with 32% gallium, somewhere here. So we expect less of a shift because it goes only from here to this stabilization energy. And in fact it does. And finally we go to close to the crossover. Now Fermi energy should not shift because it's almost saturated already. And in fact it doesn't. We irradiate very heavily. It's irradiated very heavily, but the band edge remains unchanged. And eventually we go to the gallium nitride, and we see that in this case, you don't see it here, but the band edge doesn't change because now these states are here. So we see this onset of the new absorption here from valence band to the states here. So it's completely different behavior at this stage because stabilization energy is in the band gap. So how do we explain it? Maybe I briefly tell you about this. The way it works really that defects in semiconductors have this interesting property that they can be donors or acceptors. But whether they are donors or acceptors depends on where Fermi energy is located with respect to stabilization energy. So this is the valence band edge. This is towards the conduction band. So conduction band edge of indium nitride is here. It's 0.7 electron volt from here to there. So you see that formation energy of this donor-like defect is very low here. And this is what they are mostly for. Until they reach this level of stabilization energy, and at this point it will be stable and Fermi energy would not move at all. This is very well studied in gallium arsenide, and it is known that this is how it behaves. So of course in indium nitride, the stabilization energy is in the conduction band, so we have very high conductivity in fact. Whereas in gallium nitride, gallium arsenide, the stabilization energy is in the gap, in the middle of the gap, and then it is high resistivity material. So there's a big difference. So now the question is, the problem was to make solar cells, we need to have N-type material, which is other material is always N-type. But can we make it P-type? Can we make junction? So we thought about this for quite a while, and then did a lot of effort in really trying to synthesize the material, to grow material P-type dope. And of course the question was, is it possible at all? So in gallium nitride it's difficult to dope, and the reason is that when you try to dope material P-type, you have to move Fermi energy down, somewhere close to the valence band, because this is where P-type conductivity is. Unfortunately, if you start to move it from the stabilization energy, you have a bigger and bigger chance to produce defects, because once you produce defect, it compensates this activity and you gain energy. So it's like a self-damaging process for sample. So, but we know that in gallium nitride you can dope it so heavily that Fermi energy can be here. And we thought, okay, so if we have the same Fermi energy in indium nitride, we should have P-type. And in fact, I will not have time to talk about it. After many efforts, we doping P-type with magnesium of indium nitride, we have P-type material. So we have all these components of solar cells. However, the problem is, maybe I'll skip this one. The problem is following. Even if you make solar material P-type and N-type in the bulk, the problem is surface. Surface always has defect. But because on the surface you cannot eliminate defect, this is something which is natural feature of the surface. So of course if you have defects on the surface, they will the Fermi energy would like to be high above the conduction band. It means that you have accumulation on the surface. So there is a large layer of large concentration of electrons. And say you dope material p-type, so your Fermi energy in the bulk, in the inside material, is close to the valence band. However, on the surface still it inverts, so it's inversion, because in this case the surface is still donating electrons. And so if you want to do anything with this p-type, measure Hall effect or measure somehow properties, p-type properties, you always have this n-type layer on the surface which really makes your life difficult. And this is one of the still remaining big issues for this technology, the surface inversion layer. So now I will not talk much about the effort on indium gallium nitride multi-junction cells and so on, because in the meantime what happened is that there was a quite significant discovery of potential of integration of indium gallium nitride with silicon. And silicon, if you can integrate something with silicon, that's great, because silicon technology is so well developed that there is no, it really attracts attention. So when you look at as I mentioned, the indium nitride, or in general nitrides, have a very low conduction band edge. So basically electron affinity is very large, conduction is very low. Conduction band is very low. So typical semiconductors have electron affinity about 4. So gallium nitride has 4, gallium arsenide has 4. Silicon is slightly less, but still it's much, much higher. So if you take now, you can have this very interesting situation now. The silicon band gap is 1.1 electron volt. So the valence band of silicon can be matched with the conduction band of material with certain composition, and in this case is 45% indium. So, and this alignment is very unusual, because it means that the n-type conducting material can be aligned with p-type conducting material. And so that was an interesting possibility. However, problem was now you have to grow gallium indium nitride on silicon. And this is not an easy task. And we spent a lot of time trying to improve this, and we're still working on this. So basically you have this lineup here, perfect lineup. And that's very good, because you can make now a tandem cell, which is basically n-type silicon, p-type silicon, and then on type, again, n-type indium gallium nitride and p-type indium nitride. And you have no barrier here. Because in normal, even in this very well-developed multi-junction cells, problem is this tunnel junction here, to get the good conductivity. But we have perfect junction here, and this is the great advantage of this system. And now it's really progressing very rapidly, and this is an area of kind of prototype development for this material. And so what could we get from such system? So we did some calculations. These are more realistic calculations. These are not detailed balance calculations. These are assuming some material properties, realistic material properties. So you see that if you take indium gallium nitride with the gap of about 1.7 electron volt, and silicon, on silicon you can get efficiency 35%. And this is only 2 junctions, and it is very simple in the sense that you don't have to, and that you use silicon, which is very inexpensive substrate. And this is a great advantage. So as I said, it's a very rapidly developing area, and there are several laboratories in different countries working on this right now. So, but before we now work on this, we said, what would happen now if you just make n-type on the, let's say, n-type silicon. Now, n-type was silicon on p-type indium gallium nitride. In this case, I think it doesn't work. So basically, in this case, let's say you have n-type silicon. So Fermi energy is very high here. you have p-type gallium nitride of this composition. So you have huge separation of Fermi energy. If you put them together, these two junctions, you have situation like this. So this is kind of very interesting concept. It's a single junction tandem. For any tandem, you have to have at least two junctions. And in this case, you have basically, you have p-type indium gallium nitride on n-type silicon, and you have this charge separation, large charge separation, because electrons are separated this way, holes are separated this way, and these holes are recombining with these electrons, and this is the really very, potentially very interesting concept. There is an issue here how this interface looks like between indium gallium nitride and the silicon, because these materials are not so compatible, but in fact there is quite good progress in this area. So we did the junctions like that, and first to test if our assumption was correct. So we grow n-type indium gallium nitride on p-type silicon. So normally when people say if you grow p on n or n on p, you should have a rectifying junction. But we knew that it should be perfectly optic, and it was. So it was a really good tunnel junction. However, kind of counterintuitively, when you grow n-type silicon on n-type indium gallium nitride, this is there's no change in type of the conductivity. We have rectifying properties, and this shows the rectifying properties. This is ID characteristic, current versus voltage. And it shows, so it's kind of, because we found this junction here at the interface because of this unusual alignment. So all this technology, however, even in our version of this, are quite expensive, in fact. So there is a lot of effort for concentrators. And concentrators work the way you have a very expensive material, so you don't want to use a lot of this. So you have this huge parabolic mirror. So basically light is coming from here, and then your cell is here, or array of cells is here in this point, and you focus it. And you can use, with this type of arrangement, you can get the magnification up to probably 400 times. And there are some other also which you can get higher magnification. And this is very important because in this case, people believe that this is an essential part of the technology is to concentrate light to use less material. In this case, so any ideas which could help increase to manipulate light, because you only have to manipulate light before it reaches your cell, and would be definitely very useful. This, of course, requires tracking. So you have to, because sun is moving, so you have to track sun. The other aspect of this, it is, of course, much better in direct illumination, but there is no clouds, so it always works better in states like Arizona or Nevada. So let me finish this part, kind of so we have what I said is basically we developed the several kind of ideas about how to use gallium-indium nitride, gallium nitride type of solar cells, and we currently most of the effort in the world concentrates on making solar cells with the energy gaps about 1.7 to 2.2 electron volt. And because this is the kind of where you can use in tandem with other systems and also with silicon. And there are some issues still there, and the surface, as I mentioned, surface inversion of the surface is a significant issue for this, but there are people working on ways of facilitating the surface. So how do we look this time?
So we spent 30 minutes right now. We could continue for 15 more, or?
No, I could continue. So basically now, because the other part is somewhat longer. So basically, I was talking about the multi-junction cells. So in this case, of course, you use this 3-junction cell. However, you may remember that I also mentioned that there is another concept. This is called intermediate band cell. In this case, instead of using few junction, you are using basically, you have a semiconductor with one gap, and you introduce a narrow band inside. So basically, in this case, you can absorb light of different energies with this transition between different states in the valence band, conduction band, and the intermediate band. And this is basically increases the total amount of light absorbed, and the open circuit voltage or kind of performance is determined by this large gap, because intermediate band is separated, is isolated from the rest. So and the calculations show that this is really a very promising system, because if you look at this, this shows efficiency as a function of the lowest band gap. So this band gap between intermediate band and conduction band, this lowest band gap. So if you take, and it depends on dependence, but maximum is around 0.7 electron volt. So if you have this transition 0.7 electron volt, and 1.93, which is the lowest, the whole band from valence band to conduction band, is 9.3. So the rest is, of course, 1.2, about 1.2 here. So this configuration gives you really large efficiency, much larger than the tandem, typical tandem. And this is very promising. Have a problem, and people were working on this very actively, trying to find, and there is a lot of activity going on. However, the problem is, to find the intermediate band with proper properties which would satisfy all these conditions. So we, for quite a while, worked on semiconductor materials, which we call highly mismatched semiconductors, and I will tell you a little bit about this. So, as you know, semiconductor materials have this interesting property that you can mix them. If you mix them, you change the properties from one to the other. And the best way is, of course, to change it continuously. And so there is a, let's say, example here of you have gallium arsenide with energy gap 1.4 electron volt. And you can add phosphorus, replace some of the arsenic with phosphorus. So you are producing gallium arsenide phosphide, mixed crystal. So the band gap nicely goes up to phosphorus direct gap. At some point, indirect gap here comes out. So there is, but everything is, in fact, linear approximation is quite good here. So there is some deviation, but this is small deviation. You can take also group 2,6 material like zinc sulfide selenide. Again, in this case, it's the energy gap in zinc selenide goes continuously in a nice manner to band gap in zinc sulfide with small deviation from linearity. So these materials are easy to grow; they can be prepared easily, and the reason for this is that what you do, you replace very similar elements. So let's say in gallium arsenide phosphide, you replace arsenic with phosphorus. So if you look at their electronegativity, this Pauling scale electronegativity, they are the same. If you look at their atomic radii, they are very similar. So this replacement is very small perturbation, very small perturbation. The same is with zinc sulfide selenide. You replace selenium with sulfur, and again, electronegativities are the same. The Bohr radii are slightly different, but very close. So this is why we call it well-matched alloys. You can mix them very well. However, what would happen if now you take arsenic and replace it with nitrogen? In this case, you see that the electronegativity is significantly different. Bohr radii of nitrogen is much, much smaller. The same is here. If you take selenium and replace with oxygen, again, the change is huge. So the question is, can you do it first? And then, second, what would happen? How these materials will behave? And this issue was started maybe by now, probably like 12, 15 years ago, where someone in Japan synthesized gallium arsenide nitride. Basically, he was able to put some nitrogen, replace some arsenic with nitrogen. And what happened is, it was something interesting, because all of a sudden, if you have gallium arsenide, it's the energy gap of 1.4 electron volt. Gallium nitride has an energy gap of 3.4, so it should go up. But instead of going up, the band gap collapses. Basically, it starts to go down very dramatically. As you see, this is only 4 or 5% of nitrogen, and the band gap dropped by half an electron volt. The same is with zinc selenide with oxygen. You put a little bit of oxygen, and band gap, instead of going up to zinc sulfide, it goes down drastically. So it means that this material behaves completely differently. So there were, and it was a lot of work done. This is interesting property because you can see that under some circumstances you can have material, if you add a little bit of indium here, you can have material which has very gap much smaller than gallium arsenide, but it could be lattice matched to gallium arsenide. And this in fact led people to use it for so-called vertical cavity surface emitting lasers, and this is a successful business right now to making this laser because you can move it to frequencies which are 1.3 and 1.55 micron. So it was a success of this. Instead of, despite the fact that it was so successful already material, people didn't really understand what's going on, why it's such a big change in the band gap, in the wrong direction. So we, at some point, we thought about this, and we knew that nitrogen, when you introduce nitrogen in material, so this is gallium arsenide conduction band. This is not parabolic conduction band. We knew that nitrogen introduces localized level. So this is this line here. You put some nitrogen in, it produces localized level. So if you put more nitrogen, of course, if you start to alloy it, then, so what's happening in this original state of the gallium arsenide interact with these nitrogen levels, and the band is split into two parts. Basically, and this is called so-called band anti-crossing. Basically, it's called quantum anti-crossing. Two quantum interacting states cannot cross each other. They repel each other. And this is what's happening here. And this is a simple expression on lower band and upper band. So we, at this point, we were excited because we said, oh, great, we have narrow band, we have intermediate, because we have valence band somewhere low here, we have conduction band here, and we have this band in between. It was a little bit too broad for us, for our purposes. So, and in fact, in the meantime, there are some other people get involved in this, and they show that it's really what's happening. This is a very low composition, 0.1% only, but you see already these nitrogen levels are cutting conduction band into two parts, this lower band and the upper band. And this is so in a sense, it forms separate new band here. Not so narrow band, but a separated band. So in this process, we knew that one of the problems with these materials is because nitrogen is so much different from arsenic that replacing it is extremely difficult. And nitrogen doesn't want to go in, basically. And when it goes in, if you do anything to heat it up or something, the nitrogen tends to form bubbles and escape. So, we have to use some non-equilibrium ways of making it. And of course, people can use it some low temperature MBE or MOCVD and produce it, but we needed to check larger range of potential materials, so we developed so-called ion implantation pulse laser mode. And the way we thought it would work is, you want to produce gallium nitride arsenide. So you take gallium arsenide, piece of gallium arsenide, bulk gallium arsenide. You accelerate nitrogen ions, so you produce the produce the damaged layer, but with nitrogen. Nitrogen is sitting there because it cannot escape. Everything is at room temperature. And then what we do is we use 1 pulse of the excimer laser and mold the top layer. When you mold the top layer, you get this. Everything is cold. Gallium arsenide is cold, but if you melt it, then of course what it does is it regrows very rapidly from the so the times are some microseconds, and you can test it with reflection study how it changes. So we have eventually material which has a nitrogen trapped in. The nitrogen cannot escape from and sometimes we anneal it even further, a little bit, not to high temperature. So we can get a good material, in fact, in this case. And this shows gallium nitride arsenide. We synthesize it by this method. So we see that when we have gallium arsenide, this is energy gap of 1.4. This feature in photomodulated reflection says where there is a gap. When we implant nitrogen, 1% nitrogen, our gap shifts down. This is as expected because the band gap is decreasing, and this shifts even more. And by this method, we can really activate about half of the nitrogen we are putting here. So some of them escapes or forms bubbles, but the quality of the material finally after some annealing is pretty good. So this is the material, this is the substrate, and this is our layer on the top. There are some defects here, this black spot. So this is a very promising method to synthesize material. So maybe we can.
Are there some questions to this part of the lecture? Yes?
Yeah, I've got a question. When you introduce nitrogen, yes, on the last previous slide, you create the damaged region. And what is the distribution of nitrogen? Is it projected range, or it's evenly distributed, or just interface?
Yeah, it's a good question. In fact, there are a few limitations in this. Basically, when you have nitrogen of certain energy, kiloelectronvolts, and energy, you can choose energy, so you can implant it deeper or shallower. However, you want to have it more uniformly distributed. So what we do, we have different energies and different doses, so we try to keep uniform profile. The other consideration here is with pulse laser melting, you can only melt to a certain depth, because obviously the power of the laser, we don't want to do it too deep because we ablate the whole thing. The sample atoms will fly away. So there is a kind of narrow range of thicknesses here we can synthesize. But what we do is we basically have implants with different energies and try to keep uniform distribution of original uniform distribution.
And what's the regular thickness?
This would be about 0.1 micron.
And the other one question is when you grow indium gallium nitride on silicon, what are the problems? Stress or interface?
There is a lot of problems, yeah. There's a whole slew of problems, but the one, of course, is it's not lattice much. So basically, gallium nitride will. So silicon is 1.111. So this is hexagonal plane of silicon, and you grow on this. In fact, you cannot grow directly. It doesn't grow very well. You grow some called buffer layer, and buffer layer helps to accommodate. In this case, luckily for us, gadolinium nitride is very insensitive to defect. So even if our top material is not such a high quality, it is not as detrimental as in the case. Because with the concentration of defects in gadolinium nitride, like dislocation density 10 to the 8 or 10 to 9, normal gallium arsenide or other material would not even work. Nothing would happen. That would be unacceptable material. Gadolinium nitride is much more forgiving in this sense. So, but this is big issue, how to grow it properly on silicon. So they're using buffer layer, aluminum nitride, gallium nitride, some buffer layer.
More questions? Yes, please.
Yeah, as I said, we tried not to have nitrogen because we implant different doses and different energies. So we can implant some dose deeper than shallower and shallower. So, but there is a gradient coming from the fact that the closer you are to the surface, the faster it can escape. So there is some, of course, close to the surface, there is some gradient of nitrogen. There is less nitrogen, basically. Because nitrogen it wants basically trapped. Wants to escape from this. It doesn't fit into it. The other, of course, the problem is that in this layer here, nitrogen makes a tendency to form bubbles. Because if you do it slowly, this is why we do it so fast. Because if you do it slowly, nitrogen is the strongest bound molecule in the universe, right? Nitrogen and nitrogen like each other very much. So once they get close enough, they form form a molecule, and then you bubbles and nothing will happen. Our material is useless.
More questions? I have a question.
Sure.
From the point of view of mass production, then one would want to use this technology not only just in space, but also for solar cells,
Terrestrial.
Yeah. So how technological and how cost effective is this manufacturing process you just described?
Right. No, I mean, this definitely is something which will be questionable. I mean, for us it was a scientific study. We wanted to synthesize it, and we wanted to synthesize as you see, we synthesize a lot of other material. So this is why we use it. For large-scale production, of course, it's not very useful because you can only limited homogenized laser beam you could use, right? So, but however, sometimes it's enough to have proof of existence. If you have to, because this material, specific material can be drawn by epitaxial techniques as well, but of course some other materials are not. Once we demonstrate that they can be made this way, there is a good chance that you can do different. But I don't think it is a practical method to produce large-scale solars.
Okay, and more questions? If not, the tank.
Easy way to compare our properties of this material grown by pulse laser melting and the, let's say, by standard epitaxial techniques. And this material is not as good. Unfortunately, we have to admit that if you grow by epitaxial technique, it's better, but we can reproduce most of the properties quite well. So, as I mentioned, it is we can improve it even further by so-called rapid thermal annealing. So it's not like as rapid as laser melting, but it is of the order of seconds, or 20, 30 seconds, or minutes, let's say. And so now, of course, we had a material which we thought it was like intermediate band material, but not exactly, because still our intermediate band was too broad. So we look at the potential candidates for our intermediate band material, and you can do it really survey very easily, relatively easily. Basically, again, you put your materials on the same scale with respect to vacuum level. So you see the conduction band edges or electron affinities of different material. This is indium phosphide, gallium phosphide, arsenide, gallium phosphide. And then, so the gallium phosphide has the largest, smallest electron affinity. And then you have the valence band here. So in this case, of course, we can introduce oxygen. Oxygen level, we know it is. In gallium arsenide was slightly above the conduction band edge. However, if you go towards gallium phosphide, if you would change the composition of gallium arsenide phosphide this way, then you could get material with oxygen level inside the gap. The same is true about zinc telluride. Zinc telluride and oxygen. In zinc, when we put oxygen in zinc selenide, we knew it was again in the conduction band. However, in zinc telluride has conduction band much higher, electron affinity smaller. Then oxygen level comes down and is below the conduction band edge. And this is a very interesting situation because right now, what will happen with this interaction? We said this was anti-crossing interaction between states of oxygen and conduction band. So now what happens in this case? So of course we can do calculations of this and predict what will happen. So basically this is kind of cartoon version of zinc telluride. It got 2.3 electron volts. It's a valence band, conduction band. Now we put oxygen, small amount of oxygen, we produce a level here. And we know where the level is because people studied oxygen, a small, very small concentration oxygen alone. So we put the level which is about 2 milli-electron volts below the conduction band. Now we put more oxygen. Now oxygen starts to interact with the conduction band, pushes conduction band away, and broadens. The level becomes a narrow band. We put more oxygen, and it broadens even more. And we see now, if we have Fermi energy here, we can have all these three transitions, right? From valence band to the conduction band, from valence band to intermediate level, and from intermediate level to conduction. So we have all this something which looks like an intermediate band material. And finally, so this is the finally, and we can change the width of the band by amount of oxygen we put in. Also, we can change because of the interaction this distance or this energy distance we can control by composition or by amount of oxygen. So we did. So this was kind of theoretical prediction. So, but we, using our PLM or pulse laser melting method, we attempted to synthesize zinc oxide telluride. In this case, we took, in fact, zinc manganese telluride because we had some kind of premonition that manganese could stabilize oxygen. Because we were afraid oxygen, we put it in, our oxygen will escape. So manganese was put on purpose, and manganese doesn't, if I go back, manganese doesn't change much here, because manganese conduction band, manganese telluride and zinc telluride is the same. So if we are adding manganese, it doesn't change much here. This distance remains almost the same. So we did this, and we implanted, in this case, probably 2% of oxygen, and use different laser fluxes. And this is the total energy per centimeter square. So basically, it is 0.15 joule per centimeter square. We see already something is happening. Zinc, this original band edge disappeared, but we have two transitions right now. And then we do it at higher laser pulse energy. We see that it's getting better quality, but it's less noisy signal. So we see now transition, and we identify this transition as transition from the valence band to intermediate band, and this is the low energy transition, and from intermediate band to upper band. And this is high energy transition. We still don't have this transition because we don't have electrons here. We need to have this transition, we need to occupy this state. So, but that was really very successful attempt. We are very happy with this because it indicated that such materials can be produced. And you see, in this case now we have a pretty narrow band, well separated from the conduction band. So then we said, okay, now in order to make solar cell, you need to have a strong enough absorption. So we look at the absorption coefficient of this, and in fact there is a strong absorption for this first transition, about at 1.7 or 1.8 electron volt. And the absorption coefficient is of the order of 10 to the 5, which is like inverse centimeters. So it is decent absorption, is very good. We cannot see this absorption to this state because there is a substrate, zinc telluride substrate, which blocks it, so we cannot see. But this absorption, of course, is very strong as well. So we have basically those two transitions quite well resolved. And that was encouraging. Right? However, we wanted also to check if we can produce any photocurrent in this case. And in fact, we could. This shows the photomodulated reflection, and we see those two transitions as expected. However, and we see that this is the absorption coefficient, but we see also photocurrent. So there is a photocurrent coming from the lower, from transition to the lower energy band, and that was a very good result in a sense. And of course, in this case, we didn't separate yet the intermediate band from the contact. So that was later one. So now we moved from this. We moved to gallium arsenide phosphide with nitrogen, because the other material had one significant problem. It's very difficult to dope at N-type, and of course you cannot make solar cells if you don't have P and N type material. So in this case, what we did in gallium arsenide, as you remember, the nitrogen level is above the conduction band edge. So it was not so good. We would like to have nitrogen level below the conduction band edge. So when we add phosphorus, so we know it's a normal alloy, a kind of well-matched alloy, conduction band goes up, and finally it comes above the nitrogen level. Nitrogen level comes up. And this is the range where we are interested in, because in this case, we hopefully could form as well this intermediate band. So we were interested in this range. I think some colors don't show. So we were interested in this range here. And advantage of this material, of course, is that this can be ground by MOCVD. So we even don't have to use pulse laser melting in this case, because it has been demonstrated that it can be done by MOCVD. And but however, we as a first try to see if we can find proper composition of the gallium arsenide phosphide, we did the same. We implanted 2% of nitrogen into gallium arsenide phosphide with different compositions. So we have gallium arsenide. This is our normal material. Now we add 29% of phosphorus, and then we add 38% of phosphorus. So now in gallium arsenide we have this lower band and upper band. Everything shifts up because if you have phosphorus, all the band edges shift up. But we see that this transition still remains, and in fact the intensity of the upper transition is becoming stronger, because the reason for this is that this is our impurity band or nitrogen band in this case, and this is kind of regular band. So this is always shows very good. This transition is very strong. So we see the transition from the valence band to this intermediate band, and from valence band to this conduction. So these are these transitions. So we could manipulate it the way we wanted, and this, in fact, this configuration, let's say 2% of nitrogen in gallium arsenide phosphide with, let's say, 40%, almost 40% of phosphorus would be really perfect system for. And in fact, now there is a lot of effort. There is a company, in fact, in Arizona, which works on prototype of this based on this material on the solar cell. And there are many issues here, proper lattice matching, and in this case, lattice matching is important because in this case, the quality of the material deteriorates very rapidly if there are lattice mismatch. So there is a lot of kind of mundane issues eventually when, because sometimes it's very much easier to make fundamental science than later make a device which works. But So there are some issues with, but very good isolation of this band has been achieved, and also there is a very significant progress in efficiencies of this cell. But in this case, I am just concentrating on the basic aspect of the material. So now, we talk about the so-called conduction band anti-crossing, because we always, both nitrogen and oxygen were close to the conduction band, and they were producing these changes in the conduction band, additional narrow band and anti-crossing and splitting. So all these effects were in conduction band, and valence band was unaffected. So the lower states, fully occupied states, were not affected. However, when we were doing this work, we thought, okay, so we know what happens if we replace arsenic in gallium arsenide with nitrogen. When we replace selenium or tellurium with oxygen, when we put highly electronegative element in place of more bigger metallic element. However, the question was, what we could do opposite? We take gallium nitride, it has nitrogen, and we replace some of nitrogen with arsenic. We go from the other side, right? Or take, let's say, zinc oxide and replace some of the oxygen with sulfur selenium. So there is a lot of combination which were never realized in this case. And so what's happening is quite interesting. This is a cartoonish version of quite an interesting phenomenon. So we were talking about this part. So we have gallium arsenide. It has a gap. Nitrogen level is in the conduction band. Now we add more nitrogen. We are moving in this direction. Of course, if you remember, the nitrogen split the conduction band into subbands. And so energy gap went down. This distance went down because this lower level has been moved down. So we understood this, what's happening here. Now, on this side, we have gallium nitride. Gallium nitride has a very large gap, 3.4 electron volt. Now we take some of the nitrogen, remove it, and put our arsenic in. Arsenic, what arsenic does in gallium nitride, right? In fact, arsenic forms level, which is above the valence band, and this is full occupied, so-called donor level, in this case, above the valence band. So now what's happening when you add more and more arsenic, in fact the same happens. The arsenic starts to interact, in this case, with the valence band and forms new band. And now the gap is measured from here to the conduction band, and of course there is a immediate drastic reduction in the band gap. So this is like two sides of the same material system. So of course we can do it in few percent here, and the rest we kind of predict what will happen in between from some kind of extrapolation scheme. However, we convinced some desperate people from England to try to grow it. and that was quite an effort on their part, I must say. And basically, I said, we were talking about they don't want to mix. So what's happening is you have to lower temperature, and you lower temperature also you force a lot of, if you want to, nitrogen or gallium or arsenic to change the growth condition. So what they did, they grew gallium nitride arsenide in the whole composition. And that was quite an achievement. It was most recent achievement. So what they did, they first, of course, on this side, there is a lot of data. This is what we did. Band gap is 1.4. This is gallium arsenide here. And there is a lot of data, so we even don't have it here. So it works very well here. It seems to work close to gallium nitride. You see, there is this drastic reduction of the band gap because arsenic level is so high. So this is a drastic reduction. However, what's happening when you try to change composition to kind of fit, going to higher composition, to higher arsenic contents, material breaks down and it's amorphous. So this red red points correspond to amorphous material. It's perfect, very good amorphous material, which is very difficult for example, gallium nitride by itself is very difficult to make amorphous. So we have a crystalline material here, we have a lot of crystalline material on this side, and in between is amorphous. And what happened is, but we have a really interesting system now, which is still open to, because as you see, we again are changing gap from 3.4 going to very low gap, and in fact the lowest gap we observed was 0.7. So we almost have the same system as we had for gallium nitride, that we can cover the whole solar spectrum. Question is how amorphous will work. In this case is still open. We don't know whether it could be used for solar application, but a good example of amorphous silicon is suggests that maybe in some combination this part could be used. So but this is a brand new, it has not been published yet, so this is the very, very interesting result. However, the point is that our anti-crossing works very well here. Of course, amorphous is a different material. We don't know really how to describe this material. It works very well here. We can explain because the band gap is going down very rapidly on this side. This part seems to deviate from our predictions, but it's still very interesting. What happens is when you take this material, amorphous material, start to anneal it, you see phase separation. So we see nanodots of gallium arsenide in gallium nitride matrix or something like that. And this is really seems to be very self-organized in some kind of superlattice. So this is an interesting, potentially interesting aspect. But it will require much more studies. So the other systems which we also look at is, again, to study this valence band anti-crossing in kind of systematic manner. We said, okay, so these are we have gallium arsenide, but we can replace arsenic with any of these elements because they are group 5 elements. So they isoelectronic replacement. So we can, we know what happens, right? When we put nitrogen in the place of arsenic, we have this anti-crossing in the conduction band. So we have new band here. However, we could put bismuth, which is very large and very different than arsenic as well, and put it on arsenic side. And then what happens, we form band, as we know, as I mentioned, here. So there is we can kind of control what's happening around conduction band, what is happening around the valence band by choosing what we substitute. So in this case, or you can put even both of them, and then you can produce the narrow bands here and there. And advantage of maybe putting both of them is that you can make it lattice match to gallium arsenide if you put it in the proper ratio. So, so what's happening with when you put bismuth into gallium arsenide? So bismuth is very large and very metallic. And arsenic is kind of middle of the road in between nitrogen and bismuth. And in this case, the electronic structure of valence band is affected quite drastically because bismuth again produces the level inside the conduction band, inside the valence band. So it starts to anti-cross. The problem is here is much more complicated because this is a 6-fold degenerate system, so interaction is complicated. But basically, the overall result is that we form one band here and the other band here. So it cuts into pieces of the valence band. So we did a lot of studies of this system because this system is interesting for some light-emitting diode application because it has less change with the temperature of the band gap. So, and we found that it behaves as expected. One kind of interesting aspect of bismuth of this system is that you have spin-orbit splitting here, and so the Bismuth has a very large spin orbit splitting because it's a very heavy element. So if you have so what bismuth produces very quickly is huge increase in the spin orbit, and this is something which was not expected. So the band gap goes down as expected because the valence band is pushed up. The valence band edge is pushed up. And the spin orbit splitting, which in gallium arsenide is about, in this case it's about 0.4. The spin orbits, or 0.35, yeah, but it's measured from here. So spin orbit splitting goes very rapidly. It's already 0.8 for 8% of pieces. So this is something which could potentially could have some application. So now, also, of course, there's a whole range of potential materials. So we start with the very well-matched material, gallium arsenide phosphide. We go to very highly mismatched material, gallium arsenide nitride. However, on the way, we can have materials like gallium antimonide arsenide. And these materials are much friendlier in a sense that it's easy to synthesize them, but you can study really very interesting properties of how this band anti-crossing affects properties of the material, because these materials can be well synthesized. So one example is gallium antimonide arsenide. When you look, they are next to each other, but there is some specifically size difference between arsenic and antimony. So if you put antimony in place of arsenic, you see that the energy gap again goes down. Basically, you add more antimony. This is a composition of antimony. Band gap goes down, and it is expected because gallium antimonide has smaller gap than gallium arsenide. However, it went down much too quicker. So this again suggested that there is some additional anti-crossing, and in fact, the gap here goes quite rapidly. For 10% of antimony, you see the band gap already went down. If you would extrapolate it to gallium antimonide, it probably would go to much, much smaller than gallium antimonide. So there is an initial very rapid change in the band gap. But it's not as dramatic, I have to admit. This is what we call sometimes moderately mismatched alloys, because the effects are much, much smaller. And in this calculation, in our estimate, there are two parameters basically. One is you have to find where is your antimony level, or nitrogen level, or something which you start with of adding. So this is the position of the level, and in this case it's valence band edge minus 1 electron volt. So this is located at this point. The only other parameter is the coupling parameter between the extended states of the gallium arsenide matrix and this state's antimony state. So this is the coupling parameter, and this parameter here is much smaller. It's 1 electron volt. In the other materials like gallium arsenide nitride, it was almost 3 electron volts. So this is the set of parameters. Once you have this, you have all band structure, and you can do a lot of predictions about properties. So this is how gallium antimonide looks like. Gallium arsenide antimonide. Sorry. So it starts from, if you go from gallium arsenide, it goes rapidly down, and then, in fact, however, when you start with gallium antimonide, the gap is 0.7. It still goes down even if you add arsenic. Normally, you would expect it would go up. So this is this anti-crossing again, much less dramatic as in other cases. But there is one interesting aspect of this, is that we know that in this case, when you add antimony to gallium arsenide, you affect the valence band. So you are messing up the valence band. So how it would change the mobility, something with very important property like mobility, and it has a dramatic effect on mobility. In fact, what you see is typical mobility, whole mobility in the valence band is like close to 100 in gallium arsenide. It could be even higher, but so, however, if you add a little bit of antimony, it's only a few percent, it drops like, and it goes to low tens. It's suggesting that something dramatic is happening. And in fact, what's happening is that if you take this band structure, it is very much affected valence band structure is affected by the fact that antimony is introduced here and interacts with the valence band. So it produces this dramatic, and that was this effect has been known for quite a while, for 20 years or so, and it also always people wondered what's happening in other materials. It doesn't happen. Why mobility goes so rapid? They thought maybe dislocations are important and so on, but in fact this is a very simple explanation. And what is interesting in this case, we don't use any adjustable parameters. Basically, this mobility is now calculated using this coupling parameter and also the position of the antimony level, which was established from the band gap measurement. So this is self-consistent picture. So now we can go and say, oh, what we are interested in. We know where antimony level is. We know where bismuth level is. Now we know how the conduction band edge goes as for different materials, a valence band edge. So we say if you take antimony, if you put it in gallium phosphide, you would have something which is isolated above the valence band edge, right? In gallium arsenide, we know it is below. Again, antimony is everywhere below, except aluminum nitride and gallium nitride. So in this case, we could, in fact, form the localized level very well above the valence band edge. And this would be interesting. However, incorporating of bismuth and antimony is really difficult. We forced many elements in unfriendly territory, but so far we were not successful in putting bismuth or antimony into gallium nitride or aluminum nitride, because these materials have extremely small lattice parameters. So big elements like bismuth and antimony don't want to go in and really. So, but we synthesized. I mean, we have some on gallium phosphide with antimony. We have gallium arsenide with both bismuth and antimony, and indium arsenide with both. So there is a lot we know now. Now, eventually we came to the end of this almost, and said, how about really elemental semiconductors? You take germanium or silicon and put tin. Tin is an interesting. It's not really semiconductors. Tin is a so-called grating. Tin has two forms. It's a grating and the and metallic tin. So there are two different phases, and it happens at close to room temperature that they transform to. There is a famous story about the tin. Supposedly, Russian. During the Tsarist Russia, Russian soldiers had tin buttons in their uniforms. So, of course, when they are very shiny, you can shine them very easily when they are metallic. So it was great, because they were shiny, they could polish them. And when they went to Siberia at some point, it was very cold. And this metallic tin crystallized into this semi-metallic form, which is gray. And they polished it and nothing happened. They were always gray. So that was very, so this was first discovery of the gray tin, which is kind of zinc blend tin form. But however, it has interesting properties. It has zero gap. It's kind of semi-metallic, but we synthesized germanium with tin, mixed crystals, and we found again that the band gap, germanium has gap about 0.8, right? So band gap goes drastically down, much faster than expected. And then, and that's an interesting material because it could be used potentially for some infrared detectors based on group 4-4. But this is a kind of a side project. We wanted to almost like I would say stem collector to prove that it also works in group 4 material. So let me summarize this, what we can do. So we have let's take, we have semiconductor with valence band, conduction band, and we can do many different things with this. For example, we can put sometimes the element at the impurity level into conduction band. And this is the case of gallium arsenide nitrogen in gallium arsenide. or zinc selenide with oxygen. This is the case. You can also use some other semiconductor, and this level of nitrogen or oxygen now will be below the conduction threshold. And this is the case of zinc oxide telluride or gallium arsenide phosphide nitride. So we can move this around. Now we can do similar stuff with the valence band. And what we have shown is that in this case we have gallium nitride and a little bit of arsenic, or we can have zinc selenide with a little bit of tellurium. So we are substituting electronegative element with more metallic element. And we have the whole array of compounds we synthesize. In fact, there is an interesting case here of gallium arsenide with manganese, which is not isoelectronic, but also has this level. And this is a famous spintonic material. There's a lot of work going on this material, and we probably understand now much better properties of the spintronic materials because of we know that it is also anti-crossing interaction. Finally, we can have a element like bismuth in gallium arsenide or antimony in gallium arsenide, which element is here. So we can manipulate the conduction bands separately and the valence bands separately or together. And then, so that brings us back to another application, which is photoelectric chemical cells. And in this case, as you know, how it works is that you have to have a semiconductor in which conduction band is above the hydrogen redox potential. This is hydrogen redox potential in water. And this is about 4.5 electron volt below the valence band. So the other, of course, valence band has to be lower than oxygen redox potential. And this is about 5.7 below the vacuum level. So these are the kind of conditions on this, on the location of the conduction and the valence band. Because what we want to do is we want to get electrons to this redox potential and holes to this redox potential to split the water. The full reaction is again the water plus 2 holes. Is 2 hydrogen, ionized hydrogens, and the oxygen, right? But to neutralize hydrogen, you have to get electrons have to go to hydrogen, redox potential, hydrogen redox potential. So the total reaction basically produces hydrogen, neutral oxygen, and it is done by light. And so, of course, in our case, we have we claim we can manipulate the conduction band edge, we can move conduction band edge, we can move the valence band edge. So we can engineer properties of semiconductor to hopefully fit this. And if you look at some of the semiconductors which could be manipulated this way, so again, these are redox potential, hydrogen and oxygen redox potential. So we want to have conduction band above, but not too far, because if the gap is too large, there is no light absorbed, and that's useless as well. For example, that's the case of gallium nitride, case of gallium nitride. Conduction band is already pretty close to the redox potential. Valence band is much too far, and we know that when we put arsenic, we push the valence band very rapidly up. So in adding by some arsenic, we can really satisfy better condition, because the light now will be absorbed, of lower energy will be absorbed, but still we preserve the condition of the proper alignment of redox potential. And then there are some other cases as well which we can manipulate the conduction and move conduction down. So, for example, oxides. Oxides are a good example of materials which have always conduction band sometimes close to the good position, close to the redox potential. However, valence bands are very, very deep. And there is a whole array of potential substitution in the oxides, substituting oxygen with arsenic or phosphorus, and move the valence band up, reducing the gap, and hopefully coming up with material which of much better properties. So the zinc telluride is one of the examples opposite. When we know that we can make zinc oxide telluride, we can add oxygen to zinc and push the conduction band down, and it would be a good material. One of the issues here, of course, among variety of these materials is that in addition they have to be stable in water. So basically if you shine light, most of the materials corrode very rapidly. Because of they corrode because of the, if you split water, you put a hole into the oxygen redox potential, and then in this case you are breaking the bonds, and then it etches away the surface. And so, however, if you have oxygen or oxide already, that's or nitride, which is very strongly bound material, there's a much better chance that they will be stable in the water and work this way. So this is examples of potentially useful materials. In this case, this gallium arsenide phosphide by pushing this nitrogen level down, and zinc telluride by pushing the oxygen level down production band, so to get into. So in gallium arsenide, there is in gallium arsenide nitride system is another interesting possibility. Now we could add, as I said, we would like to have gallium nitride with antimony. We were able to produce gallium nitride with arsenic, so we pushed the conductor valence band up. But still, we are not close enough, because when we want to add indium to this, the conduction band goes down and eventually falls below the redox potential, and we don't want this to happen. So we have to operate somewhere in this region, where redox potential, where the conduction band is above the redox potential of hydrogen. However, antimony would be better because it pushes it more here, so we could operate still at 1.6 electron volt. This would be good agent, and still have redox potential below the conduction band edge. So there are many options, and I mean we are now concentrating on this one because we have, as I told you, we synthesize gallium nitride arsenide in the whole composition made, and this is the active area. We were not able so far to synthesize antimonides. So again, it comes to the point that we may try to use it for different purposes as well. And in this case, of course, there is I mentioned to you that there was one of our tandems which we are working on is just silicon, PN junction, and gallium indium nitride on the top. This was our objective. But in fact, if you take any silicon, if you add any gap, any material with the gap about 1.7 or 1.8 electron volt, you would produce very good tandem with very good efficiency. So silicon is 1.1, this is the low energy gap, and this is let's say 8. So the problem is nothing much for silicon. There is gallium indium nitride is, you can do it because it doesn't care. It can be the low quality. However, if you want to do any other 3-5 material, it's always lattice mismatch. However, we could use again our manipulation of the band edges. And in this case, it would be gallium phosphide nitride with antimony. In this case, nitrogen pushes conduction band down. The antimony pushes valence band up. So we can make gallium phosphide lattice match to silicon, because it's so close to silicon in fact already. But it could be lattice match and with proper energy gap. So there is some effort right now to try to make this tandem, which would be lattice match and to silicon. And so I guess my kind of message is that you could this highly mismatched alloys is a new class of materials which are really give you a great flexibility in manipulating band structure and hopefully use it for different applications. And this basically shows how specifically it would look like, what band structure would look like. and with band gaps. We can create band gap for 1.8 electron volt. There are some obviously issues here that these are alloys. Alloys in general have properties which are inferior to compound semiconductors and non-alloy semiconductors. And as you saw, for example, mobility is very strongly affected. Mobility in gallium arsenide and antimonide, they went down drastically, cold mobility. So these are the issue of transport in these materials. However, as long as we have large absorption coefficients, so we can absorb in very thin films, then it is probably still acceptable for some applications. So let me now kind of briefly, I don't know how much time it is.
Actually, a little bit over, but...
No, sorry, I don't have to do it, but I wanted to mention to you something very important. You may hear.
Feel free to...
Yeah. Of course, the question is, we are proposing all these different elements in different configurations and so on. When you go to real application, right? You want to produce terawatts of power. It is not something that you can make with small amounts of material. So the question is, which arises very often lately, is do you have enough elements to do it on Earth? So for silicon is good. Silicon, there's a lot of sand on Earth, so you can produce as many cells as you want. However, if you think about indium already, that's becoming a little bit problematic. So people from our lab came up with this kind of graph which shows this is basically energy gap of different materials. So like selenide or any possible materials. Of course, as you know, to get the maximum efficiency, conversion efficiency, power conversion efficiency, the gap should be around 1.5, 1.4, somewhere here. So there is a bunch of material here which have proper gap. Unfortunately, they are so lousy material that you cannot do anything with that. Lately, in fact, people are talking about iron sulfide. Iron sulfide should be somewhere here, right here. So it is good material, but of course it has proper gap. But can it be useful? Can you make, especially can you make the junction and the transport properties and so on? So iron sulfide is so-called fool's gold because people. Somebody said when our lab came with this idea of using iron sulfide, they said, "Fool me once, shame on you. Fool me twice." So basically, this came because some Russian groups proposed it many years ago, and they could not do anything with this. So lately, hopefully, with some new method, they will be able to do it. But of course, and the one idea is that iron sulfide is great. There's a lot of sulfur, there's plenty of iron, so this is good material, right? But we also came up with this graph, which basically annual electricity production in terawatt hours. If you use all material, and there are two groups of material. One is probably there are different estimates, basically. There is economic reserves, known economic reserves, and the annual production, because how much you produce